This is Jack Jackson with the video solutions to practice test 1A for college algebra. The A part of exams and practice tests are designed to be done without a calculator, so I'll be working this without the use of a calculator. The way I did this is I just went through and pulled up the practice test and then just didn't answer it, so you'll see everything marked wrong. That's just because I didn't answer anything. And then just so that when I could review it, the answers would be here. And we're going to be going over each question here. So the first one is talking about interval notation and set builder notation. This is set builder notation. This is read the set of all x such that -2 is less than x, which is less than 2. So it's both, x's have to both be less than 2 and greater than -2. In interval notation, that is written as the open interval from -2 to 2, like that, with parentheses. Notice that it's basically the x is between -2 and 2, and we do not include the endpoints, so we use the parentheses. If we use brackets like this, then that would be the set of all x such that -2 is less than or equal to x, which is less than or equal to 2. So that's set builder notation. And I would graph that like this on a number line. The actual one as an open dot at those 2 points, and then solid line in between there. This keeps erasing when I do it that way, but okay. Now the textbooks, some textbooks will use a mark on here like the interval notation, and that's what this is doing. So you'll see B is the correct graph there. Next question. Next question is very similar. Notice it's between -4 and 4. We don't include -4, but we do include the 4. So bracket on the 4, open parentheses on the -4, and that's going to look like C here, from -4 to 4, open on the left, closed on the right. What property is illustrated? D times 1 is D. That's called the identity property. 1 is called the identity element for multiplication, the multiplicative identity property. Find the distance between 2 points on a number line. Well, the distance between a point x1 and x2 is the distance between those is the absolute value of the difference. So -79 minus a -7 absolute value, that's -79 plus 7, which is -72, and the absolute value of that is 72. So it's a distance of 72. Okay, so you can think of that. If -7 is here, -79 is over here, that distance will be the absolute value of the difference. Simplify some basic expressions here. -3 x to the -3 times 9x to the -6. Of course, this is implied multiplication everywhere. -3 times -9 is -27. X, when you multiply two things with the same base, x to the n times x to the m, you end up adding the exponents, n plus m. So this would be x to the -9. It didn't say it here. Simplify, I think, is a little vague, but in this problem they want you to write it with positive exponents. So this would be -27 over x to the +9. Remember, x to the -n is the same thing as 1 over x to the +n. Next question. Again, use some basic properties of integer exponents. P to the 6 times q to the -6, p to the -1 q squared. So first of all, I'm going to flip the negative exponents. So this one with the negative exponent of -1 is going to flip up to the top and become positive exponent. This one's going to flip down to the bottom, be q to the +6. The ones with the positive exponents stay where they are. And when we multiply two things with the same base, we keep the base and add the exponents. So that's p to the 7th over q to the 8th. Next question. if I have negative 6x to the negative 18th, z to the 18th, and raised to the negative 3, let's do this in a couple of stages here. Let's leave the negative 3 out here. There's more than one way to go at this, but I'm going to do it this way. I'm going to put the z to the 18th stays where it is, but the negative power on the x makes it go to the denominator. Now we have a negative power here we're going to turn into a positive power, but when we do that, then we flip this fraction over. Those negative power flip everything they have. Now we raise, since this is all multiplication, we raise each part to the third power. We have a property of exponents that says a to the n to the m is a to the n times m. So that allows us to multiply these powers. 3 times 18 is 54, so this is x to the 54th, z to the 54th. And we got to do 6 cubes. 6 times 6 is 36, times another 6, 216. And 3 negatives multiplied together is a negative. So let's put that out front. And that's how they have the answer there. Next question. Scientific notation. Scientific notation, what you do, well, let's just count the 0 on the front doesn't count. Let's count the ones after the 0. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 of these guys, and then a 1 and a 9. So we're going to move the decimal 11 places over there. So you always start with a number that's not 0, then the decimal, then the next numbers, okay? And then you say times 10. Well, if we started with this, we're going to move the decimal back to the left, so that's a negative power, and we're going to move it 11 places. So that's 1.9 times 10 to the negative 11th. On your calculator, that may show up as 1.9e negative 11 like this, but this is not really an appropriate way to write it. This should be written this way when you write it by hand. So, there we have it. Next question. Okay, solve an equation. 3x minus 5y equals 5. We want to get y by itself, okay, because we're solving for y. So we've got the y has a negative 5 attached to it by multiplication and a 3x attached by addition. Undo the addition first. You undo things in exactly the opposite order of operations of what you would do if you were evaluating an expression. So we're going to undo this by adding its opposite to both sides. That'll get the 3x to cancel on the left. And of course, that you have to do the same thing to both sides. Now we're going to divide both sides by negative 5. And so we get y equals, well, we could leave it like this, but I think they probably want this distributed. So I'm going to leave that as 3/5 x minus 1 and put it in that form. Of course, to get the 3/5, you're going to use the little fraction key here on the side. Name the irrational numbers. Now, rational numbers, remember, are numbers that can be written in the form of a fraction with integer numerator and denominator, no zero denominator. And they can also be written in the form of a decimal, and that decimal will terminate or repeat. So, irrational numbers are numbers that are decimal numbers, places on a number line, but they're not put in the form of decimals that terminate or repeat. Now, if we look at the pattern on I, for example, that is a pattern to it, and we can continue that pattern on forever, but it's not a terminating pattern or a repeating pattern. So I is an irrational number. So you got a 1/8, then 1 2/8, 1 3/8, 1 4/8, 1 5/8, and so forth. Radicals typically give us irrational numbers. Sometimes they work out nicely, like the square root of 25 is just 5. And so the square root of 11 is an irrational number. Of course, if we had the square root of a negative number, that's going to be an imaginary number. And so that would not even be real. So E and I are irrational. All the others are either fractions or decimals that terminate or repeat, or they could be written in either of those forms. F, when you look at it, it does have a square root, but the square root of 1 simplifies to just 1. So E and I are the only irrationals. All of the other numbers there are actually rational numbers. This one is the other way around. Name the rational numbers that are not integers. Okay, remember the integers are denoted by the letter Z, that little funky looking Z, and they are the natural numbers, 1, 2, 3, 4, etc. 0, and that makes the whole numbers, and then their opposites, -1, -2, -3, and so forth. So those are the integers. So -20, 0, 1 are integers. 9.09 is a terminating decimal. It's not an integer, so that would be one of the rationals. It's not an integer. Square root of 14 is irrational. Square root of 100 reduces to 10, which is actually an integer. 5 1/3 is a rational number. It's -7/48 is a rational number. And let's look at this next one, the last one. 4, 5, 4, 5, 5, 4, 5, 5, 5. Okay, that's a pattern, but it's not repeating or terminating, so that's irrational. So the irrational ones were the last one here, and the square root of 14. The integers were -20, 0, 1, and square root of 100. So that leaves the others that are rational but not integers, 9.09. 5 1/3 and -7/48. If n is a set of natural numbers, and you'd write it like this by hand, and w is a set of whole numbers, so n is a subset of the whole numbers, and the whole numbers are a subset of the integers, and they're a subset of the rational numbers, which are in turn a subset of the real numbers, which are a subset of the complex numbers. Okay, and they're going to let I guess we'll use a funky I like that, for the irrational numbers. Is 6 an integer? Yeah, 6 is an integer. And it says it's 6 not an element of the integers. That would be false. Square root of 13 is rational. That is false. Plot -3, 3. So you find -3 on the horizontal. So you start the origin where the axes cross, go left 3 and up 3. So it lines up with -3 on the x-axis or horizontal axis, and it lines up with 3 on the vertical axis. And of course on these kind you'll actually pull this in and plot. Now this you have to plot it by actually plotting in the intercepts. So to find the intercepts, you have to find when x is 0 and then when y is 0 and find those ordered pairs. So when x is 0, you just plug in x 0 in place of x and solve this resulting equation for y like this. We're going to divide by -3 here and get -2. So 0, -2, and that's right here, 0, -2. Look at your scale. In this particular one, all the marks are going up by 2. So left to right 0, down 2. So that's a y-intercept. And this will be an x-intercept. An x-intercept is when y is 0. So similarly, we put 0 in place of y and solve for x. So plug in 0, -3 times 0 is 0, 0 plus 2x is 2x, 2x equals 6, divide both sides by 2, we get x is 3. So 3 zeros there, we have to find that. That's halfway between the 2 and the 4 here on the axis. You have to plot those 2 points. It's better to get a bigger picture like this, and you can move these points around when you're plotting it. Now this is a line. We haven't really talked so far about why we would know this is a line. You probably knew it was a line from your earlier courses, but it tells us it's a line. So when you're graphing this, one of the things you have to do is choose the line tool from one of the tools over here on the side when you're working this problem. And then once you choose that, you can put the 2 points. And I think on this one it requires you to put the 2 points as the intercepts, even though you might get the line right by putting 2 other points, like say a point here and a point down here. I don't think it's going to count it right. I think you're going to need to graph on the axis like it asked you for, I think. Alright, y equals x squared minus x minus 2. Now, if you know more about quadratics, you may have an idea what the shape of the graph looks like ahead of time, and that might allow you to eliminate some things very quickly. But the idea at this point in the course is to just make a table of some x's and y's here, for example, and we can work this out. So if x is 0, we plug in 0 here, like 0 squared minus 0 minus 2 is negative 2. Try it with 1. 1 squared minus 1 minus 2 is also negative 2. And try it with negative 1. Negative 1 squared minus a negative 1 minus 2 is 1 plus 1 minus 2, which is 0. 2 squared minus 2 minus 2, that's 4 minus 4, that's 0. And then, let's see, either 3 or negative 2 should give us the same thing as well. Negative 2 squared minus a negative 2 minus 2 is 4, plus 2 minus 2 is 4. And 3 squared minus 3 minus 2 is 9 minus 5, which is 4 also. So that gives you some points, and just check, see which one of these has those points. Okay, so we've got several points to check. Let's first check and see 0, negative 2. Well, that right by itself narrows it down to D, because this one doesn't go through 0, negative 2, and neither do those two. So, in fact, we could have just gotten that 1 point, and that would have been enough. Okay, but if we check, it does go through these other points. 2, 0, negative 1, 0. You can kind of see that there. And check some of these other points as well. It does work. Is this correspondence or relation, is this a function? Well, for it to be a function, every first coordinate in the domain must go to exactly 1 second coordinate in the range, and that is correct in this case. Every arrow, there's only one arrow emanating or originating from each point in the domain. Same question here. The answer is no, because the z has 2 arrows coming out of it. That's a repeat on the first coordinate. That's what's not allowed for a function. How about this one? Okay, here we have a relation. It's a set of ordered pairs. Is it a function or not? Okay, look at the first coordinates. Negative 5, 5, 7, 6, and negative 3. There are no repeats there, so it is a function. What's the domain? It's the set of all first coordinates. Negative 5, 5, 7, 6, and negative 3 in any order should be there. The range is a set of all second coordinates, which is just ones. We can have a repeat there. So this is clearly a function, but not a one-to-one function. Okay, and you can find the domain and range whether it's a function or not. So let's just do the domain first. 15, 25, 40, 15, and 60. When you're writing a set here, remember the domain's a set. You don't list the 15 twice. Notice we do have a repeat there on the 15, so it's not a function. What about the range? 7 and negative 9, again 7 and 3. So 7, negative 9, and 3 is the range. So this one's not a function, but we do have a domain and range that we can find there. Okay, so we have a formula, P of x equals x cubed minus x. What is P of 8? You take 8 and place it in, put a parentheses, everywhere there's an x, put 8 in that parentheses and then simplify. Okay, no calculator. 8 times 8 is 64. 8 times 4, 32. Carry 3. 6 times 8 is 48. 4, 9, 50, 51. So that's 512. And we want to subtract 8 from that. That is 504. So that means 8, 504 is an ordered pair that's in our table on our graph, so forth. The answer, though, is just the 504. The graph is shown. Find h of 3, h of 5, and h of 6. So these are y values when the x values are given. So the given value is 3. That's the x value. We want to find the y value there. That is h of 3. Well, let's look at the thing here. First of all, let's check our scale out real carefully. Looks like negative 10 to 10 on both. Looks like we're going out by ones. So we want to find 3. 1, 2, 3. Find the y there, which is negative 1. Similarly, h of 5. 1, 2, 3, 4, 5. Go up here. Y value is 3. And h of 6. 1, 2, 3, 4, 5, 6. Go up, and the y value is 2. And so negative 1, 3, and 2 are our answers. Is this a function? Well, if it passes a vertical line test, it is a function. If you can graph vertical lines here, and every graph either doesn't touch the graph at all, or it touches the graph exactly once, then it is a function. If there's even one place where the graph touches a vertical line more than once, then it's not a function. So this one it passes a vertical line test, so it is a function. Yes, no repeats in the first coordinate. Find the domain here. So we start by assuming that the domain is, we assume that the codomain is the real numbers. And we assume that the domain here is the largest possible subset of the real numbers. So it's a subset of the reals. So that we get a real number for the output. So in other words, start with thinking of the domain being all real numbers and throw out the bad stuff. Well, what could be bad stuff? There are basically two things that we've talked about. Taking an even root of a negative gives us a non-real answer, and dividing by 0 doesn't give us anything. So notice we do have division here. We can't divide by 0, so x is not 0. So the domain is all real numbers except for 0. In interval notation, that would be negative infinity to 0, union 0 to infinity. And I think they're wanting interval notation here. In fact, they say that. So that's how you would write your final answer. Notice there's no problem with adding 7. The only problem is with dividing, and the only problem with dividing is with that, with dividing by 0. By the way, notice that the x is 0 is what's not allowed in the domain. The domain is everything else. Okay, next question. Graph the function using this window. Okay, well, we can do that by hand. And use it to estimate the domain and range. Well, we know that the square root of x minus 3, we've got an even root. That's a second degree root. So what's under there, the radicand, or the thing underneath the radical, underneath the square root, has to be positive or 0, but not negative. So that tells us that x has to be greater than or equal to 3. So the domain in set builder notation is the set of all x such that x is greater than or equal to 3. Or in interval notation, 3 to infinity, never include infinity, we do include the 3. So 3 to infinity, well, they did it in set builder notation this way. So that's D, so do that first of all. So that means when we're doing our table, x's and y's, we want to check 3, that's an endpoint, but anything below 3 will be undefined, and we might try some things here. 3 minus 3 is 0, square root of that is 0. 4 minus 3 is 1, square root of that is 1. There's some other ones that turn out to be nice. 7 works out nicely. 7 minus 3 is 4, square root of that is 2. Next one that would work out nicely is 12. 12 minus 3 is 9. Square root of that is 3, and so forth. But the point is as this gets bigger, as this goes towards infinity, this goes towards infinity as well. So we see that the lowest y we're going to get is 0 for the range, and the highest, there is no highest, it goes on up forever, so it's 0 to infinity for the range. It turns out that when you graph these points, you get something that looks roughly like this. I'm sorry, that's correct, but that's the wrong place. That's not the axis. This is at 3, 0. Axis is over here somewhere. And it goes up. So, and then of course they even showed you the picture, which was nice of them. And using the picture we can see, oh, there's nothing to the left of 3. It starts as 3, it goes to the right forever. Starts at 0, goes up forever. We worked that one without the picture, but with the picture helps. What's the domain here? Well, the domain here is all reals. There's no problem with multiplying by 4. There's no problem with subtracting 5. And there's no problem with an odd root. An odd root of a negative is negative. An odd root of a positive is positive, and so forth. So you can take odd roots of every real number. Even roots give us a problem. So this will actually go from forever left to forever right. What about the domain here? This is an even root. So the thing underneath there, 9 minus x, has to be positive or 0. So 9 is greater than or equal to x, or in other words, x is less than or equal to 9. In interval notation, that's minus infinity to 9, including the 9. Never include the infinity or minus infinity. So that's B there. Next, f of x is x plus 2. G of x is x squared minus x. So we use two different letters to generate two different formulas. Of course, f and g are just different labels for y, or the output. And we want to do a new function, f plus g, that's a new function, and evaluate it at 5. So that's just f of 5 plus g of 5. So we do those separately. F of 5 is 5 plus 2, which is 7. G of 5 is 5 squared minus 5. That's 25 minus 5, which is 20. And 7 plus 20 is 27. So f and g do their individual things there and give their individual outputs, but then at the end we combine them by the operation of addition. So you could similarly do this with operations of abstract, multiply, divide, any of those. Okay, so now we're going to do, well, here we go. Same thing as I just said. F plus g, F minus g, F times g, F divided by g. And we want to do this sort of as a formula. So we have f of x is 4x squared minus 2x plus 5. And we have g of x equals x cubed. Notice the domain here is all real numbers, okay, for these. So the first thing, if we're going to do any kind of combination here, we would have to overlap the domains. Well, the overlap or intersection of the domains is all reals. The only one that we have to worry about the domain then is going to be the division one. So we can simplify f plus g of x is f of x and then plus g of x. And we can sort of reorder this. X cubed plus 4x squared minus 2x plus 5 is sort of the standard way to write that. Okay, and the domain's all reals there. Okay, we can do f minus g, f minus g of x. That's f of x minus g of x. that is 4x squared minus 2x plus 5 minus x cubed, so maybe minus x cubed plus 4x squared minus 2x plus 5. And again, all real numbers work for that, negative infinity to infinity. Fg, in other words, f times g of x is 4x squared minus 2x plus 5 times x cubed. Now let's go ahead and distribute 4x to the 5th. Then we do it here. It's minus 2x to the 4th plus 5x cubed. And again, all reals work for that. And the last one, f over g, or f divided by g of x, is f of x, 4x squared minus 2x plus 5, over g of x, x cubed. Notice that we cannot let x be 0 here. So the domain's not all real numbers, it's all real numbers except for 0, which in interval notations like this, negative infinity to 0, union 0 to infinity. Notice 0 is not included in either endpoint, either interval there. Alright, so we've got functions f and g given by these graphs. What's the domain of f? Okay, so the domain of f would be the possible input values for f. So if you look at that, that goes from 2 to 14 and everything in between. The domain of g is what gives you green points. Look at all these x coordinates. So just look down here on the x-axis. They go from 1 to 11, including 1 and 11 and everything in between. Now, what's the domain of f plus g? It's got to be the overlap of these, because you got to be able to find both of these. So notice we couldn't put in numbers between 1 and 2 because they're not, f is undefined, and we can't put in numbers bigger than 11, but between 2 and 11 both are defined. So these are overlap between 2 and 11, including 2 and 11. So that's your domain. So just for practice, let's see what f plus g of let's say 7 is. F plus g of 7. That's f of 7 plus g of 7. So f of 7 is the output when x is 7 on the f, which is the blue one. That output is 6. G of 7 is the output on the green one, which is 4. And those add up to be 10. Okay, next one we're going to do composition. F of x equals 2x minus 1. G of x equals x squared plus 2. So when we do f compose g of x, that is f of g of x. So what we do is we take g of x, which is x squared plus 2, and take that output and put it in place of the input for f. So that goes in place of the x in the other one. We can simplify it. Say 2x squared plus 4 minus 1 is 2x squared plus 3. Okay, there it is in general. And of course, now we can take that formula and do f compose g of 2. So it should be 2 times 2 squared plus 3. So that's 4. 2 times 4 is 8. 8 plus 3 is 11. Okay, now actually, since we didn't have to do this for a bunch of points, it might have been easier just to do it for the one thing, for the 1 point. We could have done it this way. Here's f compose g of 2. You take 2 as the input, and the output of the first stage is, after you apply the function g, is g of 2. So g of 2 is 2 squared plus 2, which is 4 plus 2, which is 6. Then that's 6, so that 6 is the output the first time. The 6 becomes the input for the function f. Okay, so the output there was going to be f of 6. So that's 2 times 6 minus 1, that's 12 minus 1, which is 11. So ultimately, of course, these will be the same. The output for the first one is the input for the second. finally, we started with an input of 2 and we ended with an output of 11. So the function that takes you from 2 to 11 is f compose g. Notice it works. So f compose g of x. Notice it works this way. You started with an x, then you apply g, then you apply f, going right to left. So f compose g of 2 was actually 11. Okay, similar problem. F of x equals 5x plus 4. G of x equals x cubed. Find f compose g of negative 1. So we start with negative 1 on the left. We first apply the function g. G of negative 1 is negative 1 cubed, which is negative 1. So the output is negative 1. Then of g, but then that output becomes the input for the function f. F of negative 1 is 5 times negative 1 plus 4, negative 5 plus 4, which is also negative 1. So that turns out to be negative 1 at the end. And so it's kind of boring, everything's negative 1 there. Okay. Looks like we've reached the end of the questions. So that's it for that one. I'll come back for the video solutions to practice test 1B in the next video.